Starting with number 1, it says how many kilograms are there in 3,302 milligrams. Okay, now we're going to do a conversion here. We're going from our milligrams into our kilograms. So we are going from a smaller unit to a larger unit. So we know that when we go from smaller to larger, we're going to divide. Main thing here is we have to have our conversion factors. Now, we might not know how many kilograms are in a milligram, but we should know that 1,000 milligrams equals 1 gram, and we should know that 1,000 grams equals 1 kilogram. And this will give us our conversion factor that we need. Okay, so we always start with the number in the problem, which in this case is 3,302 milligrams, and then we just use our conversion factors. If milligrams is on top, we put milligrams on the bottom. So we put 1,000 on the bottom. Milligrams equals 1 gram. We use that, goes away. Grams is now on top, so we put 1,000 grams on the bottom equals 1 kilogram on the top. And we go ahead, and what we'll see is we're going to end up dividing by 1,000 twice, or dividing by 1,000,000, which we should get an answer right around 0.0003302 kilograms for our answer, which we can see it is a much smaller number than what we started with. Alright guys, moving on to number 3. It says how many seconds are there in 677 days. Okay, so again we're doing another conversion factor, and we're converting from days into seconds. Okay, now when we're looking at this, what we know is we might not know how many seconds are in a day, but we do know that 1 day equals 24 hours. Okay, and we should know that 1 hour equals 60 minutes. Okay, and we should know that 1 minute equals 60 seconds. Okay, so what we're doing is we go ahead and we start it just like any conversion factor or any conversion. We have 677 days. Okay, we set it up. If days is on top, we put days on bottom. So 1 day on the bottom equals 24 hours. Okay, we used it, so it's gone. Okay, there's hours, so we put hours on the bottom. 1 hour equals 60 minutes. And then we see we have minutes on the top, so we put minutes on the bottom. 1 minute equals 60 seconds. And then all we end up doing is multiplying 677 times 24 times 60 times 60. And we should get an answer right around 5.849 times 10 to the 7th seconds. Now if you don't put it in scientific notation, that's fine. You can just leave it in the regular numbers and plug that into the computer. It says express a length of 28.72 meters in kilometers. Okay, so we're going from meters to kilometers. Okay, when we look at this, we know that 1,000 meters equals 1 kilometer. Okay, so we always start a conversion with the number the problem gives us. It gives us 28.72 meters. Since meters is on top, we put meters on bottom, which is 1,000, and 1 kilometer on top. That's our conversion factor. We go ahead, units cancel, and we end up dividing by 1,000, which we should get an answer right around 0.2872 kilometers. The student measures the mass of a beaker filled with corn oil. The mass reading averages is 209.0 grams. Since the mass of the beaker is 11.34 grams, what is the mass of the corn oil? So this is the mass of the beaker plus the oil. So all we have to do to get the oil by itself is we just take our 209.0 and subtract our 11.34 from it, and we would get just the mass of the oil, which should be 197.66 grams. So it goes with the previous problem, number 6. It says, what is the density of the corn oil if the volume is, and it's 117.0 cubic centimeters. Remember that cubic centimeters equals the same thing as milliliters. Okay, so either way, it's a volume. We see cubic centimeters or we see milliliters. It means the same thing. Okay, when we're looking for density, our equation for density equals our mass divided by our volume. Okay, we calculated the mass in the previous problem of the oil. It was 197.66 grams. And then we have the volume, which we have right here, which is 117.0 cubic centimeters. So all we have to do is go ahead and divide this out, and we would get an answer of 1.6894, and our unit would be grams per cubic centimeter, or G over cm3. Okay, moving on to number 9. It says the volume is measured experimentally as 4.4 milliliters. What is the percent error given that the correct value is 4.16 milliliters? Okay, so what we're doing here is we're doing a percent error equation. So we know that the percent error is going to be, the equation is going to be our accepted value minus our experimental value, or our measured value, divided by our accepted value. And we're going to take the absolute value of this, and then we're going to multiply it by 100. Okay, so in this equation what we have, our accepted value is going to be 4.16 minus our measured value, which is 4.4, divided by our correct value, or our accepted value of 4.16. We're going to take the absolute value of that, multiply it by 100, and we should get an answer of right around 5.769% error. Now the main thing we have to make sure of here is make sure that we are subtracting first and then dividing. Okay, when you plug in the calculator, make sure you put parentheses around the entire numerator and the denominator to make sure that we do that correctly. Okay, on to number 11. It says, keep in mind the rules for significant figures, carry out the following calculations. Now, rules for significant figures, anytime we are adding or subtracting, we will round to the least number of decimal places. So the way that we can look at this, we see that 64.72 has 2 decimal places, and we see that our 1.4148 has 4 decimal places. So the least number of decimal places is going to be 2. So we will round everything to 2 decimal places. So our correct answer should be, when we plug all this in the calculator, we mark out 2 decimal places, should be 66.13 grams. Okay, and we know that this is the correct answer because it is rounded to only 2 decimal places, because in addition and subtraction, so it's the same thing for subtraction, you do to the least number of decimal places. It says, keep in mind the rules for significant figures and carry out the following calculations. Now what we can see here is we have our division, okay, and division and multiplication are the same. So when we're dividing something or multiplying something, when we're using significant figures, we will always use the least number of significant figures. So in looking at both the numerator and denominator, we see that the numerator has 1, 2, 3, 4 significant figures. And we see that the denominator has 1, 2, 3, 4, 5 significant figures. Okay, so when we round, we are going to round using 4 significant figures, because that's the least number of significant figures. Okay, so we plug everything into a calculator and then we mark out 4 significant figures, and we see that the correct number should be 2.430, because if we count these, and this is the unit is gram per milliliter, but we count these out, we see that we have 1 significant figure, 2 significant figures, 3 significant figures, and 4 significant figures. Okay, so division and multiplication, we use the least number of significant figures. Moving on to number 15, it says convert negative 1 degree Celsius to Kelvin. Now, whenever we're converting from Celsius to Kelvin or Kelvin to Celsius, the one thing we have to remember is that Kelvin can never be negative. Kelvin is based on an absolute 0 scale, so we can never have a negative Kelvin. So in looking at this, what we see is if we want the Kelvin temperature, we take our Celsius and we add 273. Now remember that it's opposite of that. If we're looking for the Celsius temperature and we have the Kelvin, all we do is we subtract 273. But in this case, we'll be using the first equation. So all we're going to do is take our negative 1 degrees Celsius plus 273, and we see that we would get an answer of 272 Kelvin. On number 17, it says convert negative 41 degrees Celsius to Kelvin. So what we're going to go ahead and do is, we know that anytime we're trying to find Kelvin, we always take our degrees Celsius and we add 273 to it. So we go ahead and plug everything in. We have negative 41 degrees Celsius plus 273. And we go ahead and plug that into our calculator, and we should get an answer right around 232 Kelvin. Okay, number 19, it says which of the processes, chopping broccoli, boiling water, or melting silver, involves chemical changes? Okay, now when we're looking at the difference between chemical and physical changes, chemical changes are going to change what the substance is. Okay, it's going to change from one thing to another. Physical changes are going to just alter the state of matter, meaning making it from a solid to a liquid to a gas, or breaking apart into its pieces, but it doesn't change what it is. Okay, to look at the physical changes of water, we wouldn't actually change what water was. But if we were looking chemically at water, we would break water apart into its different particles, and then it's no longer water. Okay, so if it changes what it is, it's a chemical change. So if we look at chopping broccoli, we see that if we take broccoli and we chop it up into fine little pieces, we still have broccoli, it's just in smaller pieces. Okay, if we take water, liquid water, and we boil it, it turns into steam. But chemically, it's still H2O. It hasn't changed anything, it just changed the state of matter. So that again is physical. Okay, if we look at number 3, melting silver. If we take silver and we melt it into liquid silver, well, we still have silver. It hasn't changed what it is, it's just changed its state of matter. So all 3 of these are going to be physical changes. So the correct answer that we should get is none of these. Okay, now on number 21, it says which diagram best characterizes a pure substance that is a compound? When we're looking at this, the main thing that we have to look at is, remember that pure substances are made of compounds and elements. Okay, and an element is just one single solitary atom that's all alone by itself and it's not bonded to anything. Now, the compound is going to have 2 or more atoms bonded together chemically. Okay, but for it to be a pure substance, that compound has to exist as just the compound. Okay, so if we had table salt, okay, NaCl, it's a compound and it would be a pure substance if the only thing that was in the container was NaCl or table salt. Okay, so in looking at these, we can already see that number 3 is not a compound. Okay, number 3 is going to be an element. It is a pure substance, but it's not a compound. Okay, because we can only see that it has one color atom. So that's definitely out. Now when looking at number 1, we see that yes, it is a compound, and the compound is made up of 3 light atoms and 1 dark atom. And we see that each one of the compound within it is exactly the same. So we know that this is a pure substance and it is a compound. And we see the same thing over here. Different compound because it's made up of 2 light atoms and a dark atom, but it's a compound and everything within its container only contains 2 light and 1 dark bonded together. So the correct answer for this problem should be number 1 and number 2 only. Okay, moving on to number 23. It says the smallest particle of an element that can be identified as the element. This is the definition of an atom. Okay, it's the smallest particle of an element, meaning we can't break that element up into anything smaller, and if we did, we would destroy what that element was. Okay, so for it to still have the identity of the element, the smallest thing that we can go to is a single atom. Okay, moving on to number 25, it says an example of a heterogeneous mixture is, and we have water, bronze, concrete, and brass. Okay, when we're looking at these, we have to know the difference between a heterogeneous mixture and a homogeneous mixture. Okay, a heterogeneous mixture means that we can see the particles within the mixture. Okay, we can see the things that are actually mixed within it. Okay, a homogeneous mixture means that we cannot tell the difference. When we look through it, we can't see little pieces floating around, or we can't see anything within that mixture that kind of stands out on its own. If we look at these, water is actually all by itself. It's not a mixture. Water would be considered a molecule, okay, or a compound. Bronze, on the other hand, if we look at bronze is a metal. It's a mixture of metals. But when we look at it, we don't see individual pieces of the metal within the bronze. Okay? If we look at brass is the same thing. It's a mixture of metals. Okay? But we don't see the individual flakes of the metal, of the different metals within that mixture. But if we look at concrete, and you look at concrete, you can see the particles that are in it. You can see the little rocks that are in it. You can see the different particles within that mixture. Okay, so concrete would be an example of our heterogeneous mixture. Okay, number 27, it says in the periodic table the number 14 above the symbol silicon represents what? Now, on our periodic table, the numbers that are on the very top in the boxes representing each element, we know that that number is going to be our atomic number. And the atomic number, which is the number above the symbol, always represents the number of protons in the atom. Okay, remember that the periodic table is arranged by increasing atomic number or by increasing protons. Okay, and within a single element, we cannot change the number of protons. We can change the number of neutrons and we can change the number of electrons, but protons always stay constant, and that's how we can tell the difference between each individual element. So in looking at our answers, we know that the number of energy levels in one silicon atom, that's not correct. The mass of 1 mole of silicon, that's not correct. We know that that would be our atomic mass. And then number 4, the number of neutrons in one atom of silicon. Okay, remember neutrons change from each individual isotope, and it says the relative mass of one atom of silicon is that's not correct answer. So number 1, the number of protons in one atom of silicon would be the correct number, or the correct answer, because it is the atomic number, and that is the definition of atomic number, the number of protons. Okay, on number 29, it says identify the isotope that the atom with, it gives us 12 neutrons, 10 protons, and 10 electrons. Now, the main thing here, and it's the first thing that we have to look at to kind of narrow it down, we know that in the periodic table that it is arranged by the number of protons. Okay, so if we look at the number 10, and then we look on the periodic table, we know that number 10 corresponds with neon. because that's the number of protons it has. So if I look through here, what I can do is I erase or get rid of all the symbols that aren't neon. Okay, so the only choices that I have are neon 22 or none of these. Now the 22 number right here is important because this number in nuclear symbol notation represents the mass number. And the mass number is always the number of protons plus neutrons. Okay, so when we're looking at this, what we can try to figure out is we have to make sure that it matches. We have 10 protons plus 12 neutrons, which gives us a mass number of 22. So the correct answer would be number 5, which is neon 22, because it has a mass number of 22, it has 10 protons, so we know that it's neon.